Hello friends, welcome you all to the 21st session of ARM based development. So in this lecture we will cover the coprocessor instructions. Okay. So in the last session we saw how any coprocessor is interfaced with ARM, okay, and what is the signal interaction between them. Okay. Now in this talk I will cover specifically about various types of instructions that are supported. Okay. Now based on the coprocessor, these instructions can be redefined. The mnemonics can be different, but they all fall under these three categories what I am going to be showing. Okay. So these are the three categories of instructions which we will be talking about today. So any floating point coprocessor or a DSP coprocessor or any other encryption coprocessor, anything, they need to fall under the instructions, they need to fall under any of these three categories, and they have freedom to use these three categories to put in their particular instruction, which will be given along with the ARM instructions. Okay. So the tool which is the assembler which is compiling which is assembling these instructions need to be aware of these instructions, and then they will generate equivalent encoding based on what ARM has defined. Okay. So with this introduction, let us go into the instruction format and then various specific details about instructions, and then we will touch upon the fundamental three categories of instructions. Okay. So coprocessor data processing instruction. The name itself clearly says this is something to do with the specific functionality of a coprocessor. Okay. So we are back into again the 32-bit format of instruction. Okay. So it is the condition code is similar to what we saw in ARM instructions. The same coding, okay, which was followed in ARM is followed here also, and then this is unique pattern which distinguishes that this is a coprocessor instruction. Okay. Once the ARM processor looks at this pattern, the shaded portion which are in blue, this is all not meant for ARM processor to encode, decode. Okay. So this is all specific to the coprocessors. So as soon as ARM looks at this, it will not even look into these bits because it can't make out anything from this because it is very specific to the coprocessors which are taking this instruction and processing it. Okay. And then this is another unique bit pattern which differentiates between the CDP instruction, data processing instruction, and then which one I will be showing at the end, register transfer instruction. So between ARM coprocessor and ARM. So based on this bit pattern, it decides that this particular instruction is coprocessor instruction. Okay. So as I told you in the last session, while the ARM is decoding it and trying to understand this instruction, the same instruction is being decoded by the coprocessors also, and then when this instruction enters, okay, any instruction enters the execution stage and then this condition code is satisfying, then ARM will generate the NCPI signal, if you remember. Okay, it will make this low to indicate to all the coprocessors in the system that there is one coprocessor instruction which I have found and which is in the execution stage, and then the coprocessors inform back with the CPA, that is coprocessor absent and coprocessor busy signals, to indicate whether it is any of the coprocessor willing to take that instruction or not. Once they take it up, then ARM goes forward. If it is a data processing instruction, it goes forward, but if it has to be there for servicing some instruction, it will stay there in the execution stage. We will talk about that, okay, in this instruction. Now, when the CDP instruction is seen, it is supposed to be handled by, this is supposed to be handled by the coprocessor. So once some coprocessor takes this instruction, that means it responds back saying that no, I am going to take it up, and if it has to, it doesn't have to wait, the ARM processor will carry on with the next instruction. Otherwise, it will do a busy wait. Okay, I will show you the example. So the instruction is executed if the condition is true. The class of instruction is used to inform a coprocessor to perform some internal operation. So what kind of internal operation? That is specified by this bit and this bits. Okay, these are two types: coprocessor type as well as the coprocessor operation. And then this is coprocessor registers, one of the operand registers, and this is one of the coprocessor operand register, and this is the destination register inside the coprocessor. So anything appended with the C indicates that they are coprocessor registers. And what is this? This is the coprocessor number. It can vary from 0 to 15. That's why 4 bits are given. So based on this CPID, the coprocessor ID, a specific coprocessor in the system will acknowledge, saying that I am taking this instruction. Okay, and then they will know that these are the bit patterns they need to interpret, and then accordingly perform the operation. Okay, so whatever I am showing it in the color coding is, whatever I am showing it in blue is the parameters which are meant for coprocessors and ignored by ARM. Similarly, coprocessors ignores these bit patterns, and then they look at the other patterns which are specific to them. Okay, so here no result is communicated back to ARM. Okay, ARM will not wait for the operation to complete. See, it will wait for the instruction to be taken up by coprocessor. If there is a coprocessor present in the system, but it is busy because of something else, then ARM will wait. And once the instruction is taken up by the coprocessor, ARM will carry on with the next instruction. The coprocessor could contain a queue of such instructions awaiting execution. So, suppose ARM is here, a coprocessor is here, and it has confirmed back saying that okay, I am taking this instruction. Now, it need not have to execute it immediately because it may have a FIFO of, okay, it may maintain a FIFO of instructions. Okay, so whatever instructions it is reading from the data bus, okay, it may keep it in the FIFO, and then it will execute it internally. That is also quite possible. Okay, so this, why is it required? Suppose I told you in the last class also some example of, you assume that there is a floating point add, and then followed by floating point maybe subtract, and then floating point mul. Suppose these are all the CDP instructions. You agree? Because these are all something processing to be done by the coprocessor, and it will be done among using the registers of the coprocessors. It is nothing to do with the ARM registers. Okay, ARM is here. The coprocessor, suppose it is a floating point coprocessor. Okay, so these instructions will be executed by the coprocessor using the registers mentioned in the operands, which are actually inside the processor. Now, actually speaking, the ARM doesn't have to wait for this instruction to be completed. Why? Because they are all internal to the ARM, the coprocessors, and they can take their own sweet time in completing it, as long as any of the results do not affect the flow of the ARM code. Okay, ARM is executing some code, and then these are instructions. Suppose the results of this are not immediately needed to control the flow of the ARM code, then ARM can continue with the execution of the remaining instructions. But that is not possible if these instructions are not accepted by the coprocessor. Now assume there is a two-stage FIFO. Okay, only two instructions can be in the FIFO and one can be in the execute stage. Then, if suppose when these ARM instructions were executed, and then when this FAD was given to the coprocessor was not busy, So it accepts it. That means FAT goes into the execute stage, and then 2-stage FIFO may accept these instructions because FIFO will keep the instructions pending for to be executed by the coprocessor. So this will go into the FIFO, okay, and then this will also go into the FIFO. See, once these instructions are accepted by the coprocessor, then the execute stage of the ARM becomes free. Then ARM can take some other ARM instructions. Suppose they are followed by ARM instructions. They are all specific to the internals of ARM, and now it can carry on with that. So this is what I am explaining. That is quite possible that the coprocessor may have a FIFO and then they may keep accepting it. But what happens if the FIFO becomes full and still the coprocessor is not able to accept any more instruction? Then what happens? The ARM has to wait, because once the instruction is not accepted by the coprocessor, if ARM continues with the executing the next instruction, this is lost. So it should be either accepted by the coprocessor or the exception handler should be called. So if any one of this condition is true only, the ARM will continue with the execution. So there is a FIFO possible. Okay, their execution can overlap other activity, allowing the coprocessor and the ARM to perform independent tasks. So ARM is doing its own processing and the coprocessor is doing its own job. So they are all running in parallel. That we should keep in mind. That's the advantage of having coprocessors. If ARM and coprocessor are not running in parallel, then we are not having the benefit of designing a hardware specifically for processing the coprocessor instructions. CDP instructions is not available in thumb state. See, any coprocessor instruction is not available in thumb state for that matter, but I am making a statement clearly saying that these are not available in thumb state. Okay, that means in the thumb state you cannot introduce the in between a CDP instruction. CDP is a coprocessor data processing instruction. Okay, now I am just explaining the big patterns. The 21 to 31, 24 to 31, this whole thing is meant for ARM, and then 4 also is interpreted by ARM. Okay, the remaining bits are used by coprocessor. The above field names are used by convention. Okay, these are all used by convention, but the coprocessor designer can free to use it in any way you want. They can even decide to merge these two, or they can swap any other locations. But the location of this, okay, is fixed. Can you see the reason behind this? See, let us again go back to our ARM coprocessors. Okay, CP1, CP2, CP3. Now, okay, they are all sharing the database. Okay, and the address, this is the database. Okay, okay, this is memory. Sorry about these lines. Okay, this is database. So now all these databases are connected to CP1, CP2, CP3. This is the ARM. Now, why do I say the CPID is the location of the CPID has to be fixed? That is, the bit 8 to 11 needs to have a CPID. The 4 bits need to have a CPID. Why? Let me ask a question. As a system designer, okay, we are building a SoC, system on a chip. We bought the ARM IP core from ARM, okay, and this is I am designing this for company A. Okay, this company A is not an expert in DSP. Okay, they don't have the expertise in DSP, assume, and they don't have a expertise in floating point. The expertise they have it or not is a different issue, and they are not in the business of designing this coprocessor. But the company A is designing the SoC. Okay, they buy IPs from different companies and build an SoC. Okay, they make a design and give it to companies like TSMC, because this company A is a fabless company, assume. Okay, it doesn't have a fab of its own. It's not like Intel or Samsung or these companies which have their own fabs, but assume ARM is working with the TSMC. This is a Taiwan Silicon Manufacturing Company, which is a third party company which builds SoC for us, builds a chip for us for any other third party companies, and then gives a chip. But to them we need to give a design. So this company A is designing an SoC for their own application by buying IPs from different sources. Okay, they need not have to build these IPs in house, and then they build an SoC integrating the AMBA bus. Okay, that I will talk about this bus. This is also AMBA specification, which is defined by ARM. So they build this SoC using the ARM IP, maybe memory from different memory controller from different company. Okay, and memory will be outside, my controller may be inside. There may be a cache. Okay, all these things will be there, and then so many coprocessors will be there, and then they will dedicate some IDs for each of them. When different companies, so the DSP may come from a specific company, the DSP core, and the floating point core may come from different other company who are experts in giving the IPs, top IPs, which can be integrated with the SoC, and then another company may have maybe a networking based or so maybe encryption IP built as a coprocessor. They will be providing it. Now, when if the coprocessors are provided by different companies, they need to have some standard, okay, on how they are going to interpret the instructions. Why? The instructions that are going to be seen, the instructions which are going on this data bus are going to be seen by all of them. Please remember, though the DSP instructions are handled by them, the DSP instructions will be seen by this coprocessor also, and it will be seen by this coprocessor also. Only thing is, when they see that the IP ID, the coprocessor IDs are not matching with their own, they may ignore it, but they will certainly see those instructions if they are on the system, on the bus, data bus. Okay, so they need to have a common understanding that whatever bit pattern here indicates that this is a coprocessor ID. Okay, not only this, they need to also know what the ARM provides, ARM gives, what is the pattern it provides for the CDP instruction. Okay, this also should be known to the coprocessor vendors. So they, when they are building the decode logic, okay, they will putting this information in while decoding this instruction which are coming into their pipeline, because I may be building a DSP core, but I might get the instructions which are meant for this, right, other cores also, but I will ignore it if my IP, the DSP IP that I am building, is not the instructions. My DSP instructions will have the ID which are specific to my CPID. If it is not matching, I will ignore it. So similarly, they will also do, other coprocessor vendors also will do the same thing, but they need to have an idea of what is the pattern followed by the instructions, and then where they have to look for the CPID in the instruction, because the 32 bit they will be getting from the bus. So they need to know where to, how to interpret that. That is why this location of this CPIDs are fixed. Whereas once I know that it is meant for me, then the coprocessor may decide to interpret the remaining bits in the any way they want. Okay, I may have internally maybe only 8 registers. In that case, I though the ARM provides me a 4-bit pattern for each of the operand, I can restrict it to 3-bit pattern. Okay, and then I may have inside the processor, I may have multiple operations to be performed. So I cannot encode them in this limited 4-bit pattern. So I may need a more pattern for that. So it is completely implementation dependent. How they interpret the remaining part is completely implementation dependent. So we cannot now say whether they will combine this and this, or whatever order they do, it doesn't matter. But this actually is recommended by ARM coprocessor, ARM company, that okay, you can have these parameters like this, but again it is left to the developer of this coprocessor. Okay, but they need to be consistent with the where they will keep the CPIDs and then how they interpret this conditional flag. Okay, so this is a convention. Coprocessor may redefine the use of all fields except this. That's what I explained you now. CP field is used to contain an identifying number of each coprocessor. A coprocessor will ignore any instruction which does not match with their ID. So the conventional interpretation of the instruction is coprocessor should perform an operation specified in this and this field. Okay, that among the what operation need to be performed is conventionally represented in this bit position, and these are the operands, and this is these are the operands, this and this R and M, and this is the destination. Okay, so this is the convention you are free to follow if you like it. Otherwise, as a coprocessor designer, you can decide to do it the different way. Okay, I hope this is clear to you. I took little more time to explain you. Okay, sorry, on the contents are the result in CRD. Okay, that is the convention. Okay, now this looks very complex. Okay, but very easy to understand. This M clock, all of you are aware. Okay, this is a common, the main clock. So these are the different instructions in the pipeline. This is the fetch stage of the which pipeline. This is shows which pipeline. This shows ARM's pipeline. Okay, ARM. So this is the order in which the instructions are given. Okay, this is the starting address, and then the instructions are going like this. Now you see that add comes. See, time wise, time is like this. So this is the first clock cycle. Maybe after that this second, third, fourth, like this. Now add comes into the fetch first, correct? And then add moves into the decode stage, and sub gets into fetch, and then add moves into execute stage, and this sub moves into decode stage, and CDP instruction get fetched. Okay, please remember, while this is getting fetched, the same way the coprocessor also fetching these instructions. Okay, the instructions also flowing through their pipeline the same way. Now what happens when add reaches this coprocessor pipeline? Coprocessor will see that, okay, is this my instruction? Of course not. It's a add, and then the bit pattern shows that it's ARM instruction. It will ignore it, and then next who will enter the thing? Sub will enter. See, actually it doesn't have to come to the execute stage itself, because in the decode itself it will know that add and sub are not its own instruction. So it may throw that there itself. Okay, execute stage may not even do anything. Now assume CDP is coming. Okay, first time CDP comes here, it gets fetched here in this clock cycle. Fetching is done by this clock cycle. Okay, and then it gets decoded. Okay, here. Now CDP, when it gets decoded at this time, now coprocessor knows that, okay, there may be multiple coprocessors. All of them will look at the instruction, and then one of them will choose that it is my own based on the ID. Assume that this CP is 1 and this instruction is also meant for coprocessor 1. Okay, now this CP1 will pick it. Okay, it will say that, okay, I want to use it, I want to execute it. But here this is CP1. Okay, in this case here it was in decode, both decoded, and then it entered the execute stage of the ARM. Okay, similarly it should enter the execute stage of the coprocessor also. But look at the signal here. These three signals are important. Now as soon as the CDP instruction enters, that means the conditional code is satisfied, and ARM decides that, okay, this instruction should be executed. It will bring this signal low to indicate that, okay, I have a coprocessor instruction to be executed. Any of the coprocessors in the system, are you willing to take it? Now see here, this signal, the CPA signal, has become low. Okay, what does it mean? One of the coprocessors in the system has accepted that, saying that the coprocessor absent is low means it is present. So one of the coprocessors says that, oh, this instruction belongs to me, I want to take it, but unfortunately I am busy now. Why? It may be executing the previous instruction. We don't know because this before this what happened. I am not showing it here. So the coprocessor is not currently ready to take the instruction. So what happens? Can the ARM processor carry on with its own job? It can't, because until this instruction is accepted by the coprocessor, ARM has to wait. Okay, so because it is nobody has taken up it. No, one coprocessor has said that okay I can take it, but it is now busy. So what happens is this is called busy wait. So ARM waits for the both the signal to be low. Okay. Now one of them is low doesn't guarantee that this is done with that. It has to be handed over. So it is waiting. Okay. And then what happens during that time? It fetches one more instructions from the pipeline. Okay. See here. It fetches this as well as this. See this. Two instructions have been fetched after that. Because CDP is in the execute state, then there may be two stages, right? ARM is having decode stage and fetch stage. So fetch stage can have a sub instruction and decode stage can have a TST instruction. And now CDP is in the execute stage. So two more instructions are there after this. It has been absorbed. It has gone into the pipeline of the ARM, and similarly it has gone into the pipeline of the coprocessor also. Okay. Now what happens is the coprocessor now makes it low here. That means what? It is accepting this instruction now. It is going to execute the CDP instruction, whatever it has been conveyed by the instruction. Now at this moment, ARM knows that somebody is owning it, so ARM make this high. Okay, CDP instruction is accepted, so it takes the next TST instruction into execute state and makes this high. At that moment, the core which took the instruction also makes these two high. Okay, that is the way the coprocessor is designed. That means when the next instruction comes, it can make it low or it can continue to low. Okay, if suppose next coprocessor instruction is there, then it may, based on the ID, one of the coprocessor may drive the signal. But at this moment, this coprocessor which has accepted the instruction has made it high, because it should not keep it low, continue to keep it low. That okay. Why? Once it has accepted it, it should immediately bring it up, because the ARM should not interpret the next instruction, okay, to be accepted. If it continues to be low, even if the next instruction which doesn't belong to this coprocessor is in the execute stage, it may interpret the signal and then decide that okay, this coprocessor also, this instruction is also accepted by coprocessor. So these two signals should be brought to high immediately, so avoid that confusion. Okay, because this signal, remember, the CPA and CPB are driven by multiple coprocessors. If you recall, it is connected to AND gate inputs. All the CP coprocessors are driving this input, and then finally AND output of this signals are going to ARM core. So that's how the interpretation is happening. This is how the handshake happens. So every instruction, there may be the instruction which may be accepted immediately by the coprocessor, or ARM has to wait. That is what is called busy wait sequence. Okay, I hope this is clear to you. Once you understand this, the remaining timing sequence you will be able to follow easily. Now, what is the cycle time taken by this instruction? Let us go back. I said 1s and b into I. B is number of busy wait cycles, internal cycles. Okay, how it is? See, the time taken by the coprocessor is how much time the coprocessor is occupying the ARM execute stage. That's a ARM execute stage. If an instruction is occupying the execute stage of the ARM, if it is occupying for how many cycles, that is what is gets a cycle time, right? So how many busy waits are there? It waits for this, waits for this, waits for this. Three clock cycle. Okay, the ARM is waiting for busy wait for coprocessor to be free, and then it wastes one internal cycle, one sequential cycle to come out of it. Okay, See, though coprocessor has brought it low at this moment, it cannot execute the next instruction immediately, right? It can execute only here. So one cycle here goes off, the sequential cycle goes off, and then 3 busy wait cycles are happening here. So 3 busy wait cycles. So number of busy waits, that many cycles, and one internal cycle is what I am showing it as. One sequential cycle and number of busy wait internal cycles are wasted. Okay, I don't want to call it as wasting, but of course, if it is a busy wait, it is a waste only. So there is a possibility that busy wait is not there. The coprocessor is free, then this whole thing will be 0. Only one sequential cycle will be taken by the ARM. Immediately, ARM can go to the next instruction. Otherwise, it has to wait this many cycles. Okay. So B is the number of cycles spent in the coprocessor busy wait loop. So busy wait needs to be done in case coprocessor is present and is busy with some earlier operation. I think this is clear to you. ARM busy waits until the coprocessor instruction is accepted by the coprocessor. That is what that many internal cycles are spent. Okay. I hope this is clear to you. Why it has to wait so long? While the ARM is waiting for the coprocessor to accept, okay, the instruction, ARM pipeline is stalled. Of course, once the execute stage is stalled, everything else behind it also stalled. Okay. Once it is accepted, ARM continues with the execution. So because it's a data processing instruction, ARM doesn't have to do anything, because it is totally something to do with the internal operation of the coprocessor. Because the instruction has all the operands required for the data processing, and it has to be done by the coprocessor. So ARM doesn't have to do anything except for wait till it is accepted, then carry on with its job. Okay, that's why ARM continues with the instruction stream as soon as it is accepted. Coprocessor may take its own time to complete the instruction, because that is not in the control of ARM. How many cycles the coprocessor may take depends on the complexity of the instruction and how the particular coprocessor is implemented, and how long will it take is internal to the coprocessor, and it is something to do with what it is doing with its own register set. So there is nothing to do with the ARM. Okay, very good. Now what is the format? So looks complex, but see, this condition code you can mention either EQ, NE, or MI minus anything you can give. The CDP is a indicator that it is a coprocessor data processing instruction, but the mnemonics, what you want to write here, if you suppose you want to do FAD, you can do that also. Okay, it is something, these instructions are interpreted by the assembler, and it needs to have the awareness of the coprocessor. So if it has the awareness, you can put any instruction you want. It will generate the equivalent encoding for this particular processor instruction, and the P hash has to be given. This is the number. This is the coprocessor number, coprocessor ID, which will go into that location which I mentioned, 8 to 11, I suppose, in the format. This CP ID will go there, and then other parameters to the coprocessors can be left to the implementation. So there are all some coprocessor registers, and then a specific type field, and what operation to be performed. Okay, these are all very specific to the particular instruction implementation, the coprocessor implementation. Okay, so these are all typical format. The P1 indicates that this is a coprocessor ID 1, and this is a coprocessor ID 2. It needs to do a job of this data processing based on what is mentioned by this processing. This is 10 may be indicating that it's a floating point addition, or 5 may be floating point multiplication. We don't know. So it is specific to the coprocessor implementation. And then this is some type, coprocessor type, and these are all the coprocessor registers. So this is the typical example. If suppose convention is followed, the C2 and C3 are taken as operands, and this operation is performed, and the result is put into C1. Okay. Similarly, C2 and C3 are the operands, and this operation is performed, and the result is put in C1. So provided 0 is set. Okay. This is a conventional way of interpreting the instruction, but it is left to the implementation. So we have seen the data processing instruction. Now data transfer. Okay. let me explain you why these instructions are required. Okay. See, this is the ARM code. It has got a memory, address bus, data bus. This is the data bus. To the data bus, all the coprocessors are connected. Okay, data bus. CP1, CP3 need not be all. Okay, maybe see these numbers are very unique. Those I said that 8 to 11 I think are the user CPID. So maybe I need to give only this. Okay, maybe I will say CP10 and CP11 or whatever. Okay, CP10 and 11 are floating point coprocessors. So I can say that CP9. Okay, and 9 I will given. So CP8. Suppose CP8, CP9 and CP10 are the other coprocessors. Now let us just think. Memory is here. Okay, and ARM is accessing the instruction from the memory. Memory has both data and instruction. Okay. Now I told you that ARM is only generating the address for accessing the instruction as well as data. Okay. Now what will the coprocessor do? It has got its own registers, fine, no problem, and then it is getting the instructions from the ARM core. That is also no problem. It is getting the instruction, but do you think that CPU, coprocessors can do its job without communicating with the memory? It is not possible, because all said and done the coprocessors or any processors for that matter, including ARM, has got a limited registers, right? If it has to do a meaningful job, a scientific application, the data has to be maintained in the memory and then brought into the processor and written back into the processor, correct? Written back into the process memory. Sorry. So even coprocessors need some data from the memory, and they should have a facility to write into the memory and read from the memory. But I told that all the coprocessors are not connected to the address bus and they cannot generate address. Okay, and master is ARM and only ARM can generate the address and only ARM can access the memory. In that case, what happens? The coprocessors will not be able to have any of their data in the memory, correct? So to help them do that, there are some instructions which are helping them to transact with memory, but they have a limitation. They can't generate address. So what they do, ARM will generate the address for them, and the coprocessors will give the data or take the data from memory. Can you see this? ARM will generate the address. Okay, ARM will generate the address, but data will be provided by coprocessor. Either if it is the write operation, store operation. Okay, if it is storing, suppose I say data transfer I said. So suppose it is a floating point, it's a data store operation. Okay, load operation, load, okay, or store. So if load means some value from memory is copied into the register. So a load operation may be done, and then some value from memory can be loaded into the coprocessor's registers, and then coprocessor does some operation with that, and then it does a store operation to store it into the memory. Okay, so it is possible now with these instructions, but only caveat is that the addresses have to come from ARM and data will be provided by the coprocessor. So they have to be coordinated. Please remember, it can't be arbitrary, because memory is a common element. Memory is getting the address from ARM and getting the data from the coprocessor. So, but as far as memory is concerned, once address is provided, it will provide the data out. If it is a read operation, it will provide the data out. If it is a write operation, once address is given, it will expect somebody to put the data into the data bus. So there should be a close knit between the three parties. Who are the parties? ARM, coprocessors, one of the coprocessors, and memory. So when any data needs to be transferred from between coprocessor and memory, okay, ARM provides the address and coprocessor provides the data or accepts the data. You should understand this concept very well, okay. Otherwise, the rest of the session will become irrelevant. So it is a data transfer between coprocessor and memory, but address is provided by the ARM. I will tell you why it is, why the control is always with ARM, okay. But at that moment, please remember the address is generated by ARM and data is either based on the read or write operation. Data either is provided by coprocessor or accepted by the data coprocessor. Let us go. So this is the format. Now you will be able to understand. If you recall all the load, LDM and STM instructions that are provided earlier, okay, the instruction format looks similar. Okay, these are all the things which you have seen earlier in these instructions. Okay, but this will be might be different. Okay, I don't recall what was the encoding done for LDM STM, but this whole thing gives an indication that this is a data transfer instruction and between a coprocessor and memory. Okay, now let us see what are the operands which are read by the coprocessor and which are read by ARM. See, I did a color coding to say that blue color indicates that it is this bit patterns or this operands are read by coprocessor. So I said this is the coprocessor destination register. Okay, source or destination register. This is a coprocessor number. Please remember 8 and 11 between these two the coprocessor ID should be there. Now this is what? This is the offset. Offset is to do with some data operation. And what is this? This is a base register, and whether is this ARM register or a coprocessor register? This is a ARM register. Why? When I say this is the base register, then that is what is used for address generation. And who is generating the address? ARM is generating the address. So the instruction should indicate which of the registers in ARM can be used as a base register for generating the address. So it has to be generated by ARM. So it should know which register to be used. So that is given by the instruction. So this particular bit field will be used by ARM. Okay. Not only this, including all these patterns except this blue color are all used by ARM. Okay. Remember that? Are you able to understand? So only thing is because of the size restriction, now only 8-bit immediate offset is given, but it is given in verbs. Okay, that means what? Whatever is offset is given, it will be shifted by 2 bits so that it becomes a byte address. Okay, and then source and destination register is this is a coprocessor register. Why do we need to mention a coprocessor register? I told, okay, ARM is there, memory is there, and coprocessor is there. Okay, now there is a transaction, either transfer, either one. Let us simple thing. Let us load instruction. Let is there. Suppose load means what? Some value in memory has to be copied into one register in the CP1. This is load. Okay, and then now suppose write. If it is a store, okay, some register in the CP has to be written into the memory. So in some particular address. Now this address has to come from here. So ARM has to generate the address. Okay, it has to compute the address for this memory transaction. Whereas the data needs to be provided by coprocessor. So if it is a store, it will provide the data to be written into the memory. If it is a load, it will take the data given out by the memory into some register. So you need a register here which will be mentioned, that is called CRD. Similarly, for generating the address, you need a base register here, that is called RN here. Got it? So RN is a register used for the address generation, and maybe I will write it here. CRD is a destination or source register used for the data values in the coprocessor. and offset is something to do with the arithmetic. Now how it has to be generated inside how it has to be generated by the ARM. So those offset is used, and based on whether it is a load or store, this bit will be set, and whether the address, the newly computed address, can be written back into the base register or not is decided by this bit pattern. And transfer length, to just say that whether it is a single or multiple word. Okay, multiple means it doesn't know how many. Okay, multiple transactions are happening. Okay, so that will be indicated by one bit pattern, either single instruction, single transfer, or multiple transfer. Okay, one transfer length, and then whether the addresses have to be incremented or decremented, whether it has to be incremented before or after, these are similar to the original address mode that you learned in the ARM code. I hope this is clear to you. Okay, this is the very crux of the problem. Okay, you should know this is how the instruction is interpreted. Now this class of instruction is used to load LDC or store a value or subset of coprocessor register directly to memory. So you can have either one value or multiple values. I will tell you how it is done. Now ARM is responsible for supplying the memory address, and the coprocessor supplies or accepts the data, and coprocessor also controls the number of words transferred. This is very important. Okay, let me take some other color. So number of words is very important. You should remember that. Okay, that is also controlled by coprocessor. Apart from the accepting the data or providing the data, okay, it also controls the number of words. I will tell you how it is done in the next slide. Then CP field identifies the coprocessor which has to do the job, and coprocessor will only respond if its number matches. Of course, this you know. Now let us see. See, Rn is the base register. I explained to you. CRD is the field, and the n bit contains the information for coprocessor which may be interpreted in different ways by different coprocessors. So that is number of words. Okay, but by convention CRD is the number to be transferred, or the first register where more than one is to be transferred. See, I will tell you. The transaction can be a single word. Okay, in that case one register may be transferred. Suppose ARM is here, CP is there, only one register is transferred to the memory. That is one way. Another one is multiple transfer. That means multiple transfer means it may say that I will mention the first register and then from till end of that. Suppose no, it is again implementation difference. CRD, okay, CR0 to CR15. Okay, coprocessor has a 15 register, and then here you mention that the transfer has to happen from suppose CR4. Then the coprocessor, and then you say that it is a multiple transfer. Okay, n bit is set, then multiple transfer. That means it may indicate to the coprocessor that okay, starting from CR4 you till CR15 you transfer, either transfer it to the memory or load it from memory. So it is all implementation dependent. Okay, it is nothing to do with the, but you cannot say that this is how it will be implemented, but the coprocessor can internally decide how many transfers have to be done. Okay, so n bit is used to say whether it is a one of two transfer length options. Okay, so if n is equal to 0, a single transfer, and then maybe a all register starting from some particular coprocessor register. Now this will give you some understanding of how the number of transactions are decided. See, the whole thing up to this point, whatever I explained earlier is same. Okay, so we don't have to go through that pipeline. It all has some. Now at this moment, the instruction, the LDC instruction, which is load coprocessor, has come to the execute stage. Okay, of ARM. Similarly, in the coprocessor also. Now coprocessor has said that I am available. Okay, I am not coprocessor. Absent is low means it is present, and busy is low means it is not busy. That means coprocessor accepted the instruction. That means what? The coprocessor is going to do the perform the with the help of ARM. It is going to perform the data transfer. Now, see, this instruction is fetched from after this LDC reaches the execute stage. This is also fetched from the memory. This ARM is fetching this instruction. Now, from now onwards, Okay, up to this point the data is provided or accepted by coprocessor. Okay, CP data. What is going on the database is CP data. Now who is generating the address? Address is generated by the ARM and the coprocessor is accepting it. Now how does the ARM know when to stop generating the address? See, when I say that it is a multiple transfer, the address has to be incremented, right? Now please remember all the transfers are 32 bit, okay, similar to our LDM and SDM, 32 bits, that means 4 bytes. So it has to increment by 4 the address. So starting address is computed based on the LDC instruction and then it keeps incrementing it by 4. So suppose this is address 100 is generated by ARM, 104 will be here, sorry, from this onwards 100 and then 104, 108. So it is generating the addresses. Now you remember for this transfer to happen here in this cycle, the address is generated one cycle ahead. So that is why you see that this instruction is fetched during this cycle, and at that time the new address for the data transfer is happening here, and then those the data values are transacted over the bus. So who is reading it or writing this data? The coprocessor is accepting it, or it may be generating the data, but address is generated by the ARM, and then when this particular busy goes up, that indicates that coprocessor is done with its multiple transfers. Okay, coprocessor decides how many number of transfers happens. How it is done? I will erase this to give you. Number of transfers is indicated by coprocessor by keeping this busy for that many cycles. In this case, 4 words have been transacted, and it has been controlled by the coprocessor. CPB is generated by coprocessor. So by keeping it low, it informs the ARM that do not go away from the LDC execution, continue to generate the address. Okay. Please remember, it is not similar to CDP where the ARM can just, okay, once somebody has accepted it, ARM cannot go to the next instruction because ARM has got the job of generating the address. So it cannot throw this LDC out of execute stage and then take the next instruction test. It cannot do that because it has got a job to generate the address, and it will be able to generate the address only when this LDC instruction is in the execute stage of the ARM pipeline. So ARM will continue to be in the the LDC instruction will continue to be in the execute stage of the ARM till this busy goes high. That means when this happens, coprocessor indicates that okay, I have done with the transfer. Now you can stop generating the address. So at that moment only it generates the address for fetching the next instruction, and it goes ahead with the execution of the test instruction, the next instruction which was there in the pipeline. So can you understand this? The transfer is happening with the help of ARM, and data is either provided or accepted by the coprocessor, and ARM has to keep that instruction, the data transfer instruction, in the execute stage based on how the CPB is given by the coprocessor, and then the transfer completes. This is very, very important. I hope this is clear to you. Okay. Now cycle time. Can you understand this? I have explained this for the ARM instructions. So one non-sequential cycle because of what? This particular data transfer is non-sequential because this is a new address generated, and then rest of the data transfers are sequential because it is all adjacent addresses access is happening. So 1n, and then how many words are transferred? -1 is the sequential, and then this instruction was in the execute stage for one more S cycle. Okay, see here, one more S cycle it was here, and busy wait was the 0 here. Okay, it immediately it was accepted. Otherwise, busy wait also will be added. So S and n-1 S and 1n. See 1n, and then number of words -1 S. Okay, number of words transferred, plus 1s anyway for the execution address generation. Okay, so effectively this will be ns, okay, and one capital N, that is non-sequential address. First address will be non-sequential, so that is what you will see, 1n, 1n minus 1s and busy wait I. Okay, now this non-sequential address, sorry, I will tell you here how many are there. See, 1, how many cycles? 5 are there, right? 5 are there. How many words are transferred? 4 words. So 4 anyway is due to the 4 words transferred, except and then plus 1 is here, that is non-sequential. So 3 plus 1, 4 cycles are used by this instruction. Okay, so that's why you see this, but this is a data transfer. Okay, one second. Okay, so busy cycle, if it is there, then it will have one, not that many number of internal cycles, and then one non-sequential cycle followed by n minus 1. So that many words are transacted. Okay, so ARM is responsible for providing the address used by the memory system. I have explained you already. The addressing modes available are all LDM similar to this. Note however that the offsets are limited. Originally it was 12 bits in ARM mode, but in Coprocessor instruction it will be only 8-bit offset, and it is shifted by left 2 bits because the offset is given for the words, because you are very clear, we are sure that it is a word transfer only can happen, and then whether it is subtracted or offset is subtracted or added is based on this bit pattern, because plus hash you do or minus hash offset you do, that decides the addition or subtraction. So whether the calculation will be performed before or after, that is pre-indexing or post-indexing, is decided by this, based on whether you are maintaining the offset inside or outside this. So you should go back to the LDM addressing modes to recall this bit patterns. Okay, so this is how it is done, and then W is the overwritten, whether the base register can be written back or not is provided by this. The value of the base register modified by the offset is pre-index instruction is used to address the transfer of the first word. Okay, so the address computer is used by for the first word transfer. Afterwards it will be incremented. So second word will be incremented by 4 bytes because it is always a word transfer, and the address will be incremented by 1 word for each subsequent transfer. Always I told you that in the sequential addresses will be incremented, because that's how memory is programmed. So this is a general pattern. Okay, it is nothing specific. It is you can it's again application specific. So you can mention LDC or STC and then mention the conditional code and then which coprocessor ID and how to generate the address, and then say which coprocessor to copy that value to or from. Okay, so these are all some example usages of instruction. So take this as a R5 as a base address, add 24 to that and use that value to access the memory and put it is a store. So C3 is coprocessor is copied into this address, and then R5 is updated because exclamation mark is there, so write back happens. And what is this P2? This is the coprocessor P2. The coprocessor 2 is used for this transfer. Although the address offset is expressed in bytes, okay, here you can express it in bytes, but internally it will be stored as a word, because I told you that offset is left shift by 2 bits, because it's a word transfer. The offset can be right shifted and stored, and then internally ARM processor left shifts by 2 bits and uses that address. So the assembler will adjust the offset accordingly. Now there is one specialty here. Rn is R15. The value used will be the address of the instruction plus 8 bytes. Now let me explain to you this. Okay, if suppose by chance we are writing Rn as R15, suppose, then we should know that which R15 is used. it is the whatever is the PC here. Suppose this instruction is at 100, the R15 will be 108. That's all. Okay, 108 will be used as R15 value, and write back into R15 should not be used. So if you are using instead of R5, if you are using R15, you should not write back. That is a condition. Okay, assembler will give an error. It will not accept that kind of an instruction. Coprocessor data transfer is not available in thumb state. It is similar to any other coprocessor instruction. It is not available in thumb state. Okay. Now one more thing, data abort is possible in the coprocessor data transfer also. The address is legal, but the memory manager generates a abort. Okay. Now see, a abort has to be there irrespective of whether the transfer is between ARM and memory. Okay. Or the coprocessor and memory. The transfer may be between these two. Okay, but abort should be allowed because there may be that memory is currently that floating point thing is not available in the memory. Then abort has to be generated. Now who will execute the abort handler? ARM will execute, not this guy. ARM will execute the abort handler. Okay, and then perform the job required for avoiding that abort, and then restart the instruction. So it is similar to a data abort happening in the ARM processor. So the write back of the modified base will take place, but all other processes will be preserved. So if suppose write back is mentioned in the base register, okay, so that write back value will be written into the value into the register. Suppose rn hash you are given, then the base register will be written with the write back value if abort happens. After the writing the value, the abort. So it is very specific to the abort handler how you write the abort handler for coprocessor. So I am not going into the details of this because it is very specific, but I am just giving you that you have a back of your mind that a data transfer with the coprocessor and memory also can create an abort, and in that case how does the ARM behave? How does the ARM behave? If the coprocessor is partly responsible. Why I am saying coprocessor is partly responsible means because the data is provided by the coprocessor and the address is generated by three-party transfer, right? Three people are involved: ARM, memory, and coprocessor. So if abort has to restart the instruction again, if you have to restart the instruction, then coprocessor also should be partly involved in this. So coprocessor may know that this abort has happened. Okay, there may be some signal where it will come to know that there is a abort. Because the pipeline flush will happen, and similarly pipeline flush will happen. So the three parties will work together to resolve this issue. Okay, memory anyway is a dumb entity here, but ARM and coprocessor will work on this abort handling and must ensure that any subsequent actions coprocessor takes can be repeated when the instruction is retried. See, on a data abort, you remember the instruction will be retried. That means what? It will be executed again after the abort handler is completed. So we have to make sure that the coprocessor and ARM keeps the register status in such a way that it doesn't impact the correctness of the program. Okay, so don't bother too much about it, but I want you to be aware that there is a possibility of a data abort in the coprocessor transfer also. Okay, now the last register instruction type, which is the register transfer. Again, let me come back. ARM is there, coprocessor is there. Okay. Data bus is there, ARM, CP, memory. Okay. Now we saw that coprocessor can do its own job using CDP instruction. We saw that coprocessor and memory, between the memory, data transfer can happen using the coprocessor data transfer instruction. Okay. This is CDP. Inside that something happening is done by CDP. Transfer between memory is CDT, but there is one more transfer possible. Okay, that is, this is the master I said, ARM is the master and coprocessor is a slave. Okay, and I also told you that conditional execution is done, okay, based on the flags inside the coprocessor, inside the ARM processor. So if suppose you write a program, okay, let me give an example. ARM code you are written, okay, ARM code, okay, and then so coprocessor FAD you are done. Now suppose if FAD results in a 0. Okay, suppose this you are writing that register CR1, assume the FAD result is written into coprocessor register 1. Okay, suppose if it is a 0 value is written into after the end of this instruction. Okay, now down the line somewhere I want to, if okay, suppose branch, if floating point results in a 0, I want to go to some other location. Suppose I want to go to the label L1. Okay, otherwise I want to execute this instruction. See, the floating point operation is done along with the ARM instruction. So there should be some coherence. Otherwise, what is the use of having some ARM code running and the DSP code running? They need to be in sync. Okay, some results of this need to reflect on the control flow of the ARM instruction. Otherwise, what is the use of this whole thing running in a single application, right? So there should be some control flow possible based on the outcome of the operation done by the coprocessor. Now, how can it be done? Because though floating point also, maybe I am taking that example because it is very easy to comprehend. Assume the floating point is a scientific notation which I will be covering in the next class, but that coprocessor is having some flags. Okay, they also have some flags, but these flags are not accessible from the ARM code. They are internal to it. Now, how can ARM this change the control flow? Okay, without having an access to this, it is not possible. So to provide this option, there is a way that we can transfer some information across the ARM and the coprocessor. See, this is a next set of instruction that is called register transfer. Register transfer is what? Registers in ARM. Okay, ARM has got some set of register, coprocessor has got some set of register. These values can be transferred between them, but how ARM interprets the values and how coprocessor interprets the value, they are different, because here they are all integers. Okay, maybe coprocessor may be all floating point arithmetic. Okay, float. But suppose if there are some data transfer instruction converts the format and then puts it in the ARM core, then the values can be exchanged between the ARM core and the coprocessor, as well as some conditional flags. Okay, flags can also be exchanged between them. Okay, say two things. Okay, let me come back. See, flag is one thing. Okay, sorry. So flags, okay, can also be exchanged between a coprocessor and a ARM processor. In that case, what happens? Suppose I have a 0 flag here. Okay, in the coprocessor, if I am able to transfer this value to 0 flag in the ARM, okay, then what I can do? I can do this operation. If my floating point arithmetic resulted in a 0, no, I want to control to go to L1. L1 is some code which ARM is accessing. So I can control the flow of ARM based on some outcome of this which is happening. So there should be some provision for the floating point registers to be transferred, or as well as the flags of the coprocessor to be transferred to the ARM coprocessor, so the conditional flow can be effectively done. So this is the need for having this set of instructions. Okay, so let us see how these instructions help us and how is it implemented. See, there are two MRC and MCR. If you recall, there were MRS and MSR instructions earlier in ARM. Okay, what is this? Yes, it was a CPSR. Okay, transferring to some register. Okay, you can transfer the CPSR to some register. Always the convention is like this, right? So or you can do a register to CPSR. Okay, that is S is a flag register. So this was the instruction which we saw sometime back in the ARM code. So the same convention, coprocess to ARM register is this instruction, and register, the ARM register to coprocessor is this, it's MCR instruction. So the conventions are same, always it is like something R equal to C. Okay, this you can interpret as R equal to C. If you want to just remember, right, you write this, then you say R is for ARM registers. Easy to remember. C is because C it is a coprocessor register. So coprocessor register is written into ARM. This is the convention. This is ARM register is written into coprocessor register. That's all. Very simple. Similarly, S is a flag, so register is a ARM register. That was the convention we followed there. Okay. So very easy now. This instruction is not as complex as the memory transfer instruction. Only thing is the parameters are more. Okay, you may transfer. See here, CRN is a coprocessor operand. This is another operand, coprocessor operand, and then RD is a register. The RD is a ARM register. So either you may do this operation and write into ARM, or ARM will be written into some register in the coprocessor. Okay. So ARM stores a destination register. So RD is given, but doesn't mean that it is only a destination register. It is also a source register. Okay. Similarly, coprocessor also this register is a source register, source or destination. Similarly, this is source or destination. Okay. So the transfer can be between anything, between coprocessor to ARM or ARM to coprocessor. And this is another operand register. RM, CRM, where is it? It's an operand register. Okay. So it could be a load or store, and then you can even perform some operation and then transfer it. Okay. I will give you an example. Suppose there will be an instruction will be coming later. Okay. You have a floating point coprocessor. Okay. Floating point coprocessor, and this is the ARM is there. Suppose you have a value 1.0. Okay. In the CR0 of 1.0 is stored in coprocessor register 0. You want to transfer it to R0 of ARM. Okay. CP CR0. CR0 you want to write into R0. Here this is 1.0, which will become 1 here. Okay. Because it's a 2's complement notation and this is a floating point representation. You cannot have the same bit pattern here and you try to interpret this as a 1. So there should be some transition happening. This pattern has to be transferred to some format here to make this as a 1. So that operation can be performed here, mentioned here, so that the coprocessor before transferring the value it does this transition and then puts it here. Because these values how they are represented in ARM register and the coprocessor registers are different. So you cannot have the same bit pattern in both the places and expect that to work. So there should be some transformation has to be done. The transformation is specified by this particular operation mode. Okay. Okay, good. So let us see. This class of instruction is used to communicate information directly between ARM and the coprocessor. So an example will be a fixed floating point value held in a coprocessor. So this is a fix. I mentioned that 1.0 is done as 1 in ARM. Okay, this is CP. This is called a fixed operation. Fix this floating point value into an integer value. Okay, that is called an instruction which is used by the floating point processor. Okay, where floating point number is converted into a 32-bit integer, and the result is then transferred to ARM register. Similarly, a float operation is suppose 3 is here in ARM. If it has to be written into a floating point register, it has to be written into as a 3.0. So there should be a transformation that is called float. Okay, there are different instructions which are used, so we don't have to remember this, but you understand the concept. When any data is transferred between ARM and the coprocessor interprets the data in a different way, and the ARM interprets it in a different way. So they need to be transformed into the other format. That is what is achieved while transferring these values. That's all is important here. So an important use of MRC instruction is to communicate control information directly. I told you that CPSR flags of ARM, you want to change it. Okay, but let me try to see that you remember this or not. Okay, ARM. In ARM, I mentioned to you that MSR and MRF instructions are used. Fine. Okay, but you cannot have a move instruction operating on CPSR, correct? You can't say move CPSR into R1. You cannot do that. you before that what you suppose this is what you want to do, what you need to do, let me say change the color, okay. What you need to do, you will say that M S, okay, MRS R2 suppose, and then CPSR, okay. Now what happens, CPSR is copied into R2 and then you will say move, okay, directly if you want to insert in R1 you can say that, okay. Okay, why do I go around this? So R1 comma CPSR. What does it mean? I cannot access using any of these instructions. I need to use a special instruction to move from CPSR to some register value. Okay, so let me come back here. Now, what is the I told you that if you want to have a control flow, you want to change it, you need to have the flags in the CPS, no flags in the control processor to be flags here to be transferred to ARM. Okay, ARM has the flags in the CPSR to change the control flow of ARM instructions. How can that be done? There is a special way. If the RD is okay, you can use this instruction only M R C. That means what, coprocessor is moving to register. Now suppose here you say R15 as the register, okay, ARM register, and then say that the flags in the coprocessor, okay, in the C coprocessor. Now what happens is when you want to say the flags in this is moved here, whatever is the value in the 4-bit lower 4 bits, okay, of what you transfer is actually not written into R15, it is written into CPSR of, okay, CPSR of the register. The CPSR 4 bits is there, no, those 4 bits are written into. This is when you mention the transfer coprocessor register of ARM and then say that RD is R15, then what is done is it is treated as when a coprocessor register transfer to ARM has R15 as a destination register, the bits 31 to 28 of the transferred word are copied into these flags and other bits remain unaffected and PC also not affected. So it is an indirect way of saying I want to transfer the flags inside the coprocessor to the flags in the ARM processor. So what you should do? It is a coprocessor will have some set of instructions inside, so you have to execute them and then bring the flags of the coprocessor maybe into one of the registers of coprocessor. Okay, similar to MSR, there may be some instructions, so you have to execute that instruction to bring that into some one of the coprocessor registers and then transfer that to R15 of the ARM. Once you do that, what happens? The flag value has come into the CPSR of the ARM, and then we can have a code in the ARM. Say that okay, branch EQ, you can say, or some conditional check, you can change the flow of control. So you have to execute ARM in sync with the coprocessor instructions. So there is a provision provided by the ARM to perform this job. Okay. So what are the instruction fields? I explained to you already. Destination register based on whether MCR or MRC. The rest of the fields are interpreted by coprocessor. CP indicates the coprocessor ID. So register transfer. Now one more thing, if suppose register transfer if you are doing with R15 as a source register, okay. Suppose ARM is here, okay. You want to transfer MCR, suppose ARM register to coprocessor register, and suppose the register what you are mentioning as a ARM side, this is the RD, this is the source register here. Suppose you are mentioning this as a R15. So what value, okay, R15 value from here is going to the coprocessor some CP register, okay, which is mentioned by this guy. Suppose CP1, okay, register 1, sorry, CP ID, so register 1. Now R15 is going into CP, no, some register 1 of this. Then you may need that you want the current memory, okay, with the code or R15 where it is pointing at that address you want to transfer. what you get actually is PC plus 12. It's a very a good question to answer. Think about why it is so. Let me give a example. Add is there, one ARM instruction, and then you are executing MCR, okay, and then there is subtract instruction, and then there is a test instruction, and then there is one multi instruction, suppose. Now when this instruction is MCR is what registered to, and then you have mentioned that R15 needs to be transferred, okay, to some coprocessor register R1. Now when this is in execute stage, this is accessed, okay, means PC is here. Suppose this is the address under 108. Now this is also fetched, okay. Now for doing this register transfer has to happen through data bus only, right? ARM is here and coprocessor is here. The transfer has to happen through data bus, right? That means what? The instruction fetch has to be stopped for a while. So after accessing this instruction, it will be incremented by another 4, that is 1C, and this value will be written into R15, okay, and then this will be executed. So because I told you that when this is in execute state, other 2 instructions have been already accessed, and the PC is also incremented by 4. Since we cannot access this instruction, we need the data bus for transferring the value which is mentioned here to the coprocessor. We need the data bus. So the fetching of pre-fetching has to be stopped. So but instruction address would have been incremented to the next value, which happens to be this value plus 12. Okay. Now if you are having R15 as the source register to be moved into coprocessor register, what you will be getting is a plus 12 value. That is what is explained by this bullet. Okay. I hope this is clear to you. So this is the timeline. MCR is come. Okay. MCR is in the execute stage. Okay. Now it is bringing the thing low. Okay, it's a register transfer between the coprocessor and ARM processor. So ARM is delaying it by 1 cycle because it is already the memory. It needs a transfer, data bus. So it has to complete this fetch. So it is completing this fetch, and then it is making this low. By the time this also accepted immediately, then what is going on? This is the value in the register, either in coprocessor or in the ARM processor is exchanged, and then it comes back. See, please remember, this need not be completed in 1 cycle. It can take multiple cycles, because if you recall, just now I mentioned that while transferring the fixed or float, the coprocessor can perform some operation, especially when it is supposed to transfer a coprocessor value into a ARM register. It will take some time to do that. So at that time the busy wait will be more. But if it is between ARM and from ARM to the coprocessor, the register value is copied into coprocessor, and then it is performing the job. So ARM can continue with this execution during this time. So the delay will be there only when CP to ARM transfer, because CP has to perform some transformation and then send it to ARM, whereas that is not true in this case. When ARM value, it is ready, actually the integer value whatever is there is ready to be transferred to CP, and then the transformation job that CP has to do is internal to it. So ARM need not have to wait for it. So the busy cycle will be brought up, so that ARM can continue with the execution and the transfer will complete. Okay. So this is a very subtle point that you should remember. So cycle time is 1 cycle to 1 sequential cycle for the execution, and then if there is a wait, 1 B wait, and then 1 coprocessor cycle, because this is called coprocessor cycle because we are transferring between ARM and coprocessor. That is what is called a coprocessor cycle. And why is this plus 1 is there apart from busy wait? That is because I will tell you. See, it is only for RC. RC is what? coprocessor to register, right? So ARM register. So when from the data bus, when the value comes into the ARM core, it lies in the data in register. Okay, if you recall data in register, and then it will be taken into the register set. So it will involve one internal cycle to do this transfer. Okay, that's why this +1 is there only for coprocessor to register, whereas that is not there for coprocessor register to coprocessor. Okay, because the register value is put into the data out register and then immediately that is taken out. But when we are reading in something from the, it is same, is similar to reading from memory. Okay, though it is reading from a coprocessor, it is similar to reading from a memory because it is coming through the data bus. So it will take one more cycle, internal cycle, to transfer it to the register, destination register. That's why +1 is there. Okay, and then this is a format, so don't get worried too much. It is very specific to the implementation. So this is the CPID, and then you can mention the which ARM register you are talking about, and then which are the coprocessor registers can be mentioned here. So these are different type of instruction. Okay, this is the coprocessor ID 2, and we want the, this is what, C to R. That means coprocessor register, okay, perform some operation 5 on C5 and C6 and transfer the 32-bit word result into R3. Okay, do some operation based on this and then transfer it to R3. Now what is MCR? Move R4 into this, okay, and then use the both operand to do some operation based on what the value was come into it and then write into C6. Okay, so whatever value read from R4 you do this, and then this is if this condition is 2, transfer the coprocessor to register. Okay, operation is 9 and then type is 2 and it is written into R3 and use both C5 and C6. Okay, and then transfer the value into R3. That's what is the each instruction means. So with this we have come to the end of coprocessor instructions. See, these are all very a high level view of how the coprocessor instructions are provided and how they are used. Okay, you should, if this knowledge is enough, once you have this background information, then you can go into the details of any particular coprocessor implemented for ARM. Then you will be able to understand some of the instructions in the coprocessor may be implemented using one of the 3 types of the instructions. Okay, it will be encoded as one of the 3 type of instructions. Okay, so and you will be able to appreciate how the transfer is happening, how many cycles they take, how the memory, if it is something to do with the memory, how the address is generated by ARM, and how the coprocessor is interfaced with that. So I hope this talk was useful for you to understand this. And in the next class we will talk about coprocessor, floating point arithmetic asset, the representation, and then we will take a look at the vector floating point processor in the following lecture. Okay, thank you very much for your attention. I enjoyed sharing this knowledge with you. Hope it was useful and enjoy your reading and on all. Thank you very much. See you in the next class.